let's talk about the problem topic number 1. Like I said, the third law of thermodynamics. And third law of thermodynamics is something about an entropy and the reference point. They want you to calculate delta S, and the reaction is given here. Okay, and the entropy has a unit of joule per Kelvin, and they want you to calculate for particular reaction what's your delta S for the following compound. And the first reaction is nitrogen react with an hydrogen to produce an ammonia. And you have to go, and here I provide a table for you. This is a table that you can find out from thermodynamics textbook. And it is not delta S. It is an entropy itself for different matters. And you are at 25 degrees C, which is 298 Kelvin above 0 Kelvin. So you are not at 0 point. Although nitrogen, hydrogens are pure compound, pure elements, you do have some numbers. It's not 0. So it's conceptually different from the energy state. And this is an entropy. Okay, so I find this information, and what do I do is, this is my notation. Dr. Mai has a different notation in the textbook, but I like this notation. Delta S naught is a summation of all the species, okay? And just mu J is a constant. So this is for example here, this is a mu J. There's all mu J here, okay? The constant go in front of us, okay? Mu J times S naught for particular compound J. Okay? So you do it everything. And the most important information is mu J is positive plus your product. And the mu J is negative value for reactant. All you gotta do is sum it together to get the answer right. So this is actually, once you have a table, all you gotta do is, okay, I have this table. I'm gonna write mu J on the side, and the LH3, that's a 2, but that's a plus 2. Okay. And what about the hydrogen? That's a reactant, so there should be minus 3. That's a minus 1. And all you gotta do is multiply this together and add them up. That's all you wanna do. And that's is exactly follow the formula that is shown up. I guess I'm putting it in red. So this is exactly I'm performing this, multiplying that. And then you will get minus 198.3 joule per Kelvin. So that's your delta S naught for this reaction. Okay. So just for this one, I will not do the other one, but just although it's redundant, let me write this way just for refresh your memory. So delta S naught, what I wrote here is 2 times 192.5 minus 3 times 130.6 minus 1 times 191.5, and that's becomes 190 Kelvin. Okay, so this is the same thing that just the equation written in red is same as the equation written in purple. It's just same thing. And then the question is direction is favored to occur. This is actually kind of vague statement. The more direct and what scientists use is this reaction is spontaneous. Okay? That's the term that everyone is using it. The question didn't ask this way because this is not enough information. So what that means is I think they are trying to say, because you only can calculate delta S, and if delta S is a positive number, it helps to have the reaction to be spontaneous. So that's why reaction favor to occur in case where entropy is increasing. And that's the one. Okay, although this is not sufficient, but this is just a necessary condition. Okay? And so that's why they just say that way. Okay? If somebody asks, these reactions are spontaneous or not, your answer is, I don't know. Probably that's a probably bold answer to do that, because this information is not sufficient. Entropy alone cannot determine or dictate where the reaction is spontaneous. But any rate, here is favor. Favor to, oh, this not favor, right? Not favor to. Okay, so that's the first one. Okay, so let's do the second one here. Here is okay. So we'll do the same. So the constant product, this one is methanol. That's a +1. Hydrogen. That's a -2. CO2. That's a -1. Just multiply those numbers. We will say delta S naught is -332.3 joule. Okay. So delta S naught, which entropy is in a direction of decreasing. So once again, it's not favored. So this time, I think that I want to emphasize a little different nuances here. Okay. So let me pull it up here. So if you look at the value was given for entropy is a joule energy per Kelvin times mole, right? Mole Kelvin. So this is actually has to be defined for each compound. So if you have 2 moles and it will be bigger, so it is a normalized quantity per mole basis. And if you're looking at the way that this one, this mu j, this is okay. Mu j has a unit of mole, right? So if you multiply mole times joule per mole Kelvin, and that is corresponding to just a joule per Kelvin. So this is a material specific. This is, do you remember what I said last class? This is what is called a per reaction, right? Because the reaction was written in this way, so therefore this value is for that particular reaction, right? So I can interpret that as, okay, so if you want to make 1 moles of methanol, that's an entropy decrease. But if you want to use consume 1 moles of hydrogen, actually only half of this value will be an entropy decrease. Right? This is per reaction. Right? So as a reaction written, this value corresponding to, because there's nothing called mole thing stuff here, because this corresponding to 2 moles of consumption of hydrogen, that's the corresponding change. Right? So if you want to just curious about 1 moles of hydrogen change, the value should be half of this. Right? So you can use this value for answer particular question. So this one, once again, was written as it is, not to be ambiguous, just to cover 3 aspects at the same time. Okay, so once again, this is like per reaction. This is my way of writing this, but that's what it is. Okay, let's finish up the last one. Yes, I want to use a little different now. Okay, so this constant that goes in front, water is +6, 4, 7, minus 7, 2, minus 2. You add them together, delta S naught, you multiply those numbers, right? So that's exactly, once again, delta S naught is mu j, S j naught. You add them together for products and the reactant. And that's exactly what I did. And once again, this one is now plus 92.6 joule per Kelvin. This one is positive. So delta S is increasing it, and that is a favor. Okay. That's the only the differences. It's funny to say that the title of this topic is a third law of thermodynamics. I mean, it's just to show how to calculate those numbers, but conceptually they want to talk about the entropy as well.